Hi, this is Professor Jim Chen at California State University, Long Beach. In this video lesson today, we will be looking at finding vertical and horizontal asymptotes of rational functions. Let's start with the definition of a rational function. A rational function is a function of the form r of x equals p of x over q of x, where p of x and q of x are polynomial functions. In general, we assume that p of x and q of x do not share a common factor, which means that r of x is written in its most reduced form. For example, r of x, which is 3x plus 2 over x minus 5, would be called a rational function, while f of x, which is square root of 3x plus 2 over x minus 5, is not a rational function, and square root of 3x plus 2 is not a polynomial. The goal of this lesson is to study horizontal and vertical asymptotes of such rational functions. Informally, an asymptote is a line to which the graph of the function gets closer and closer to as one travels along the x-axis or the y-axis. Let's formally define asymptotes next. Let's start with the vertical asymptote. First of all, a vertical asymptote needs to be a vertical line, and all vertical line takes up the form of x equals a constant. So this first blank here is going to be x equals some constant number a. And we call that x equals a vertical asymptote of the function y equals f of x if the y value goes to something as x value goes to something. Well, let's try to figure out what these something have to be. If x equals a is a vertical asymptote, that means the function value should be really close to this line in the long run and stay close to that line as x value gets really close to the value of a. That has to be true from both directions of a, which means that if I were to approach a from the right-hand side, then the function value is going to get close to it and to stay close, either in the positive direction or it's going to be staying close in a negative direction. On the other hand, if I were to approach a from the left-hand side, then the function value should get close to this line in a positive direction or stay close in the negative directions. And by the way, we use dashed line for asymptotes. For example, in this first case, a picture could look like the following, where if this is the vertical asymptote x equals a, then the function would look like this. And in that case, we would say that the y goes to the positive infinity as x goes to a from the positive direction, or from the right-hand side. We use the plus sign to indicate it's to the right of the value a, and then read this as x approaches a from the right. In the second case here, we could have a scenario where the function value approaches the negative infinity as x approaches a from the right. In the third case here, we might have a picture that looks like this, where the y value goes to infinity as x goes to a from the left. We use the negative sign here to indicate approaching from the left. The fourth scenario here, we have, for example, a picture like this, where y value goes to the negative infinity as the x value approaches a from the left-hand side. Do you know in this case y goes to negative infinity as x goes to a from the left? In all four situations, we see that y value goes to either the positive infinity or the negative infinity as x approaches a from both sides. It allows us to come back and fill in the blanks here. A line x equals a is called a vertical asymptote for the function if y goes to either the plus or the minus infinity as x approaches a either from the positive side or the negative side. Next, let's look at the definition for a horizontal asymptote. Well, first of all, a horizontal asymptote is a horizontal line, and all horizontal line takes the form of y equals a constant. So I know for sure this is going to be y equals something. I'm going to call this something b for now. Let's investigate what the horizontal asymptote could look like next. A horizontal asymptote is something that the graph gets really close to and eventually stay close to it in the long run. So imagine a function could do something like this in the beginning, cross over, but eventually settles down and just stay close to it. If that's the case, then we say that as x approaches infinity, because y values stay close to this horizontal line b. Of course, this picture is kind of an extreme case. If we only focus on long-term behavior, then we can kind of think of the graph just really just does this or that. In both situations, I would say that y goes to the value b as x approaches infinity. On the other hand, you could also have the situation where the graph could do this on the opposite side of the x-axis, which means that function goes to the value b as x gets to the negative infinity. And of course, you can have a situation where it just kind of gets close to and it always stays below it for the whole time. It will also be the case where y goes to b as x goes to negative infinity. In summary, we say that the line y equals b is a horizontal asymptote of the function if y is close to b as x goes to positive or negative infinity. Next, let's investigate the asymptote behaviors for the well-known function y equals 1 over x. First of all, we know that the function is defined everywhere except when the denominator is equal to 0, and that is when x is equal to 0. 0 here is kind of like the a value in the vertical asymptote definition there. We would be very curious to see which one of those 4 cases we have around the value 0. Particularly, I want to know what the y value is as x approaches 0 from the right, and also as x approaches 0 from the left. A quick way to investigate that is by plotting a table of values. Start with the x value that is close to 0 but to the left of it, for example negative 0.1, and then pick a number that is slightly greater than negative 0.1 but still less than 0, so kind of squeezed in between, for example negative 0.01. Continue doing that for a few more points, so negative 0.001 is squeezed in between, and then negative 0.0001 is also squeezed in between the negative 0.001 and 0. Now figure out the y values accordingly. See that the y values grow from negative 10 to negative 100 to negative 1000 and negative 10,000. If we ask ourselves the question, as x gets really close to 0 from this side, what is the y value gets close to? Well, it shouldn't be too hard to see that this goes to negative infinity. What we can say is that as x approaches 0 from the left, the y value goes to the negative infinity. We can now do a similar table for the x values approaching to 0 from the right. Start with the value that is slightly greater than 0 from the right hand side, say 0.1. Then pick a number that is between 0 and 0.1, say 0.01. We then pick a number that is between 0.01 and 0, say 0.001, and so on. If we now investigate their y values by using the function, well, the function is 1 over x, so it's essentially doing 1 divided by 0.1 here, which turns into 10. And then we get 100 for the next y value, and then 1000 for the third y value. It shouldn't be too hard to see that the y value goes to the positive infinity as x approaches 0 from the right. We can translate that information now to the graph. We know that the y-axis is the vertical asymptote, so I'm just going to try to draw a dashed line really close to the y-axis to indicate that the y-axis is actually a vertical asymptote as well. From the first table, we know that as x approaches to the 0 from the left-hand side, the y value goes to the negative infinity. So I can kind of do an arrow pointing downwards as x value gets close to 0 to indicate that behavior. As x goes to the 0 from the right-hand side, the y value goes to positive infinity. So I can do an arrow pointing up this way as x really gets close to 0 from the right. Two tables tells you the behavior of the function when the x value gets really close to the point A. It doesn't really tell you the end behaviors as x approaches infinity on both ends. Let's investigate what happens to the y value as x goes to positive and negative infinity. Well, the function is 1 over x. Now imagine x getting really big. So as x gets to infinity, the expression 1 over some really big number eventually will turn into a very small number. So if this is very big, this becomes very small. So small that it's going to go to 0. Which means that the y value goes to 0 as x goes to the positive infinity. On the other hand, as x goes to the negative infinity, we will be using 1 over a very, very big number. So this is going to go to 0 as well. So that means y goes to 0 as x goes to the negative infinity. we incorporate those information on the graph here, then the y value goes to 0 as x goes to infinity, kind of indicated this direction. And the y value goes to 0 as x goes to the negative infinity would look something like this. And the reason why I needed to stay below the x-axis on the left here is because I know the picture from before, it has to stay below it. Those information then tells you that your picture should look something like this. And in this case, I will call the line x equal to 0 a vertical asymptote, and the line y equals 0 a horizontal asymptote. In a nutshell, function behaviors near x equals a constant a, where the denominator polynomial is undefined, gives you the vertical asymptote. And function end behaviors as x goes to infinity and negative infinity give the horizontal asymptote. Which means that to find the vertical asymptote, all we need to do is set the denominator function equal to 0 and solve for the x values. But on find horizontal asymptotes, you actually have different situations. In general, there are actually 3 scenarios where the horizontal asymptotes can be. Let's investigate that in general here. Suppose that a rational function r of x is defined to be some polynomial on top divided by some other polynomial on the bottom. For simplicity's sake, let's call the numerator function an n of x. Let's call the denominator function the d of x. Leading coefficient here is an on top, and the leading coefficient on the bottom is bm. And the leading degree, or the degree of the polynomial on top is n, and the degree on the bottom is m. First case is when the degree of the numerator function is equal to the degree of the denominator function, which means that n is equal to m. Instead of telling you what the result should be, let's investigate through an example here. Let's let n of x be 3x squared minus 2x minus 1. Let's let d of x be 2x squared plus 3x minus 2. Then we want to know as x goes to infinity what happens. End behavior is about the dominating term and what that dominating term does. And in this case, the highest power in both polynomial is x squared. It's x squared here, it's also x squared down there. Therefore, the highest power overall is going to be an x squared. To investigate this long-term behavior, we do this trick by divide every single term in both polynomials by the dominating term. And if we do that, we get r of x equals 3x squared divided by x squared minus 2x divided by x squared minus 1 over x squared, all divided by the 2x squared divided by x squared plus 3x over x squared minus 2 over x squared. We want to simplify as much as we can. Notice that 3x squared over x squared really just becomes 3, and 2x over x squared becomes 2 over x, and then the 1 over x squared stays the same. In the denominator here we have 2 plus 3 over x minus 2 over x squared. Remember, we're trying to investigate what happens as x approaches infinity. Well, if x goes to infinity, that means the quotient 2 over x becomes really small. So small that it eventually goes to 0. If x goes to infinity, that means 1 over x squared goes to 0 as well, and at a much faster rate than the 2 over x goes to 0. For the same reason, both of these terms will go to 0 eventually. So what's really left over is this 3 and the 2 in the numerator and denominator. As happens is in the long run, we get 3 over 2. Which means that the horizontal asymptote is y equals 3/2. Hopefully through this example, we can kind of see what needs to go into this dot 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 here. It turns out that the horizontal asymptote is simply just going to be y equals an over bm. An is the leading coefficient for the numerator and bm is the leading coefficient for the denominator. The other two cases follow similarly. Case 2, if n is less than m, that is, degree of the numerator is less than the degree of denominator. For example, in the case of the r of x given here, degree of the numerator is 1, degree of the denominator is 2, certainly satisfies the condition. In this case, the dominating term is x squared, because that is the highest degree appearing in all polynomials. So we're going to divide every single term by x squared. We get r of x equals 2x over x squared minus 4 over x squared, all divided by x squared over x squared, plus x over x squared minus 2 over x squared. We simplify it as before to get 2 over x minus 4 over x squared, all divided by 1 plus 1 over x minus 2 over x squared. As x approaches infinity, we notice that the first term goes to 0, the second term goes to 0 on top, and both terms on the bottom here goes to 0 as well, leaving the only non-zero term, a 1, in the denominator. Overall, we have a 0 on top over a 1 on the bottom, which equals 0 overall, which means that the function r of x has the horizontal asymptote y equals 0. And this is true as long as the denominator has a higher degree than the numerator. In this last situation, we have the reverse case, where the degree of the numerator is greater than the degree of the denominator. For example, r of x equals x squared plus 2x divided by x minus 1. But you can also do the similar trick as we do before by dividing every single term in the polynomials by the dominating term, x squared, to get x squared over x squared plus 2 over x squared plus 2x over x squared divided by x over x squared minus 1 over x squared. This reduces down to 1 plus 2 over x squared divided by 1 over x minus 1 over x squared. As x goes to infinity, this term goes to 0, this term goes to 0, and this term goes to 0. We actually have the situation of 1 over 0, which we know is undefined. And that means that you actually do not have any horizontal asymptote. And this kind of makes sense intuitively as well, because an asymptote is a number you actually approach to as x gets large. In this case, x squared term dominating is just going to change the overall function value as x becomes bigger and bigger. So it really doesn't approach to a single number, it just gets bigger and bigger as x gets bigger and bigger. Kind of a cautionary tale is that although r of x might not have a horizontal asymptote, it might still have other types of asymptotes. For example, vertical asymptote and something called a slant asymptote, which will be discussed later. I want to do just one quick example before we end this lesson here. We want to find all horizontal and vertical asymptotes for this function r of x, which has degree 3 on top and also degree 3 on the bottom. To find vertical asymptote, we solve for x by setting the denominator function equal to 0, because vertical asymptote appears wherever your function is undefined. We typically do this by factoring, and notice that there's a common term of x appearing in all three terms. If I take that out, I get 2x squared plus 5x plus 6 left over inside. And I try to factor this further by using all combinations, and you can quickly see that there is no way to actually get a 5 in the middle, which means that this is not factorable over the real numbers. And what that means is this term really would never be equal to 0. Hence, x equals 0 is the only vertical asymptote we have. For the horizontal asymptote, since the degree of the numerator is equal to the degree of the denominator, which is both equal to 3, the horizontal asymptote is simply just going to be the leading coefficient on top divided by the leading coefficient on the bottom, which in this case would be 6 over 2, and that is equal to 3.